In this section, we're going to take a first look at how electrons are arranged within an atom. In previous sections, we said that the atom is composed of a very dense nucleus, which contains the positively charged protons and the uncharged neutrons. Orbiting around the nucleus are the electrons. The electrons have a negative charge. They're very small and very fast-moving, to the point that we don't ever try to describe where the electron actually is. Rather, we talk about an electron cloud, that is, a region the electrons occupy. As we'll see in the next chapter, there's strong evidence that, much like onions or ogres, electrons actually occupy energy shells or layers. As we move out from the nucleus, each layer has more and more space and can accommodate more electrons. In the first level, we have enough space for 2 electrons. I'm going to represent these with a minus charge. So 2 electrons in level 1. Level 2 has more space and can accommodate 8 electrons. It doesn't matter where I sketch these. The idea is that there are 8 electrons orbiting around. Level 3 can hold 18 electrons, and then level 4 can hold 32 electrons total. We'll talk more about how these are arranged later. For example, fluorine is atomic number 9, which means that it has 9 protons in the nucleus. I can represent this as a +9, and it also has 9 electrons in the neutral atom. Now, we know that 2 electrons can fit in the first level, so that takes us to the second level. So this would be electron 3, 4, 5, 6, 7, 8, 9. So the second level with fluorine is not full. It turns out that most of the interesting chemistry arises from the electrons at the outermost occupied level. We refer to this as the valence level or the valence shell. So for example, we could say here the valence is level 2, and level 2 has 2, 4, 6, 7 electrons around it. Now there's a couple different ways we could show this. One way is through what we call a Lewis dot structure. In a Lewis dot structure, we're going to use the atomic symbol F to represent the nucleus and the inner shell electrons. We're then going to represent the valence electrons simply by drawing a dot for each electron. So we would say that the valence for a fluorine atom looks something like this. It doesn't matter exactly where we draw the dots. The idea is that there are 7 dots around it. Now, most of chemistry actually has to do with atoms gaining or losing electrons. If an atom like fluorine is very close to having a full valence, a full outermost shell, it will tend to gain an electron. So for example, fluorine will typically want to gain 1 electron. I could represent it on the diagram at left like this, or I could represent it in the Lewis dot structure by again drawing the fluorine with the 7 electrons around it, and then drawing an 8th electron, which will actually fill out the energy level. Now, if it's picked up an extra electron, it's picked up a charge of -1, so I would also want to show it with a minus charge. Let's look at a second example. Sodium is atomic number 11, meaning that it has 11 protons in the nucleus. I can represent this by drawing a +11 there in the nucleus. It also means that it has 11 electrons in the neutral atom. Let's sketch these in as well. Remember that 2 electrons can go in level 1, 8 electrons can go in level 2. That brings us to 10 electrons. We have 11 total, so level 3 is going to only hold 1 electron. If we wanted to represent this with a Lewis dot structure, again we would draw the symbol sodium to represent the nucleus and the inner shell electrons, and then we would show just 1 dot around it to show that there was 1 electron in the outermost shell. As a general rule, an atom has extra stability resulting from a filled outermost shell. Now in the last example, fluorine, the atom was able to gain that stability by adding an electron. In this case, if sodium loses one electron, its outermost shell, its outermost filled shell, will be level 2. And so the sodium tends to lose this electron. If we show this on the Lewis structure, we say, oh, that dot, that outermost shell and what was its valence is now gone. And so the sodium with no dots around it represents a valence which is empty, meaning that the shell just below it is actually filled. Since the sodium lost an electron, it's now going to have a charge of +1 that we can represent like this. Let's use what we know about the energy levels of electrons to answer a couple of questions. First off, in its ground state, what is the highest occupied electron shell for a chlorine atom? Well, chlorine is atomic number 17. Energy level 1 can hold 2 electrons. Energy level 2 can hold 8 electrons. Energy level 3 can hold up to 18. And energy level 4 can hold up to 32. So, with the chlorine atom, we could say how many electrons are in energy level 1, in energy level 2, and in energy level 3. Well, level 1 would be 2. Level 2 would have 8. That brings us up to 10, and that means that the remaining 7 electrons could go in energy level 3. So the highest occupied electron shell for a chlorine atom is going to be level 3. Let's do the same thing on the second example. How many electrons does a lithium atom have in its highest shell? Again, we could say, well, how many electrons are going to go in each shell? For lithium, it's atomic number 3, so it's going to have 3 electrons total. The first 2 of those electrons can go in energy level 1. The next electron will go in energy level 2. So, lithium is going to have 1 electron in its highest energy shell. Finally, which of the following has a full highest energy shell? Well, if you have 2 electrons, you're going to have a full shell. If you have 2 plus 8 is 10 electrons, you're going to have a full shell. And we could go on from there. Of these, fluorine has 9 electrons, so it would not quite fill level 2. Carbon has 6 electrons in its neutral form, so it would be in level 2, it wouldn't be full. Boron has 5 electrons, it wouldn't be full. But helium has 2 electrons, which means that it would completely fill level 1. So helium is going to be the correct answer here. As we'll see in more detail in the next chapter, the periodic table is actually organized by electronic structure, which allows us to quickly tell which atom will gain or lose electrons. As a first generalization, atoms on the left-hand side have only a few electrons in their outermost shell and tend to lose electrons. Atoms towards the right have their shells almost full and tend to gain electrons. And atoms on the far right, what we call the noble gases, neither gain nor lose their electrons because they are stable. The atoms in the first column all have 1 electron in their outermost shell. So these tend to lose 1 electron, which means they form species with a +1 charge. Atoms in the second column tend to lose 2 electrons, which means that they tend to form species with a +2 charge. On the other hand, atoms which come in the column closest to the noble gas, column 7, tend to gain 1 electron, while things in the next column, oxygen, sulfur, etc., are 2 electrons from being full. These tend to pick up 2 electrons and have a -2 charge. So let's look at another sample question. Which of the following is likely to lose electrons from its valence shell? There are a couple ways we can go at this. One, we could remember that level 1 holds 2 electrons, level 2 holds 8 electrons, etc. And we could say, is this atom closer to full or closer to empty? Another way, which may be a little bit easier, is to recognize that if the atom falls on the left-hand side of the periodic table, it's going to lose electrons. So a quick glance at the periodic table shows us that the only one of these that falls on the left is magnesium. Magnesium is in the column that tends to form +2, and so it is going to be the one that loses electrons. Finally, let's look at one last example. Write symbols, including atomic number, mass number, and charge, for atoms containing these particles. Number 1, an atom containing 4 protons, 5 neutrons, and 2 electrons. Now, first off, if it contains 4 protons, this is going to be atomic number 4. 4 protons corresponds to a beryllium atom. So we could write the symbol beryllium. We write the atomic number in the upper left-hand corner, so we could write a 4. The mass number is the sum of protons and neutrons, so the mass number for beryllium here would be 9, and the mass number is written in the lower left-hand corner. Finally, we write the charge in the upper right-hand corner. Beryllium has 4 protons, which means a charge of +4, has 2 electrons in this case, which means a charge of -2. So the overall charge is going to be +4 minus 2. That's going to be +2, and we can write that in the upper right-hand corner. Let's try another one. Write the symbol for the atom containing 17 protons, 20 neutrons, and 18 electrons. Remember, the number of protons determines the identity of the atom. Atomic number 17 is chlorine, so this is going to be a chlorine atom. The atomic number always goes in the upper left. The mass number is the sum of the protons and the neutrons. 20 plus 17 is 37. The mass number goes in the lower left. And finally, we'll put the charge in the upper right. In this case, we have 17 protons and 18 electrons. We have one more electron than proton, which means we have a charge of -1, and so we could put the charge in the upper right. So, in conclusion, electrons orbit the nucleus in layers or energy levels. Energy level 1 can hold 2 electrons, energy level 2 can hold 8, 3 can hold 18, and 4 can hold 32. The highest occupied energy level in any atom is called its valence. An atom can lose or gain electrons from its valence shell and is very stabilized if its outermost occupied shell is full. We'll talk more about this in future sections.